I recently came across this interesting piece of test equipment at a convention, and I asked National Instruments to send me a loaner model so that I could play with it a bit more and show you guys as well. So they did, but I'm not receiving any compensation for this review, and I'm also not going to charge Patreon users for this video, just to keep it as conflict-free as possible. So let's talk about what this thing actually is. This is called the National Instruments VirtualBench, and it's a whole bunch of instruments crammed into this fairly compact unit. So it's got a 2-channel oscilloscope. It's 100 megahertz bandwidth with a gigasample sampling rate. If you're using both channels, it's 500 meg for if you're doing both channels at the same time. It's got a function generator, 14-bit DAC, which is capable of arbitrary waveforms, but only through the programming interface. When you're using the bundled application with this thing, which we'll talk about in a minute, it's your standard square, sine, and triangle waves. It has a 5.5-digit multimeter, and it comes with standard probes like this, and it's capable of measuring up to 10 amps. It's also got an integrated power supply, so it has a 6-volt 1-amp supply, which is fully programmable, and also a plus 25 and a negative 25 volt supply at half an amp each. And then the most interesting part, the best for last, it has this digital I/O connector, and it has 8 channels that you can control and even send bus protocols in and out, so SPI and I2C can be read or written through this port. I almost forgot, it also has a 34-channel logic analyzer built into it, so it's a mixed mode oscilloscope. There are 2 main ways to interact with this piece of equipment. You can use the bundled application that National Instruments provides with it, and that runs on either an iPad or on Windows. And it allows you to control all of the instruments through manual drop menus in the software, which I'll show. And of course, it's a PC-based oscilloscope. However, you can also control it programmatically through LabView or through C. And National Instruments provides a C library and some example code. So the reason that I'm most interested in this piece of equipment is that you can do things like monitor the current through the power supply at the same time you're sending and receiving SPI commands through the digital port at the same time that you're using the oscilloscope to actually measure higher speed signals. So this whole unit here can function as a standalone test bench where you could put a sensor in front of it and power the sensor through the power supply, check how much currents it's drawing, vary the voltage up and down, interact with the sensor through the digital stuff, and measure the analog if you've got an analog sensor. I can see a few applications where this piece of equipment would be especially suited. So for example, at the end of an assembly line, if you want to test the boards coming off the line, you've basically got everything you could pretty much ever want here. With the power supply included and all the other things that I mentioned, you could put the board in your test jig and have this thing run through a bunch of tests programmatically. You could simulate a dying battery, you could simulate a reverse battery, you can manually simulate button presses through the digital controls and so on. And since it's all being controlled through LabView or C programming, you can write a test procedure, basically a state machine or whatever you want, and the assembly line worker only has to interact with a very clean interface, basically just hit go and the thing could run through all the tests. I think it's also very well suited for testing sensors, basically functioning as a data logger. And so your sensor might be I2C or SPI, and collecting that data through a benchtop instrument is actually fairly difficult, especially if you have to program the device, like if you have to send a SPI command and then read the data. With LabView especially, you can collect all of this and then even plot it over time. So if you want to trial a temperature sensor for an upcoming design or something, and the temperature sensor speaks SPI, it'd be great to have this thing just run all day long and make sure that it's stable and watch the temperature variation over time just to make sure the sensor is working the way you want. I should also mention the device has 2 interfaces for the computer connection. It's got a USB, and then it also has a Wi-Fi, a wireless connection. And I did a pretty cool job of designing the Wi-Fi. This can act as a network host. So you can tell this thing to start a wireless network, and then you can connect to it from your computer without adding like another router to it. Also handy if your work situation has like a corporate network and you don't want to connect to it because this isn't a certified piece of equipment, you can tell it to start its own Wi-Fi and get around it that way. There's also the possibility of putting this thing on a device that is moving, for example, a robot, and if you power this with like a car battery and inverter, you can actually communicate with this thing over the Wi-Fi and even control the robot through LabView and through the digital controls and collect data all at the same time. So there's quite a few applications where I think sort of data logging and sensor interface is where this thing is most appropriate. The instrument costs $2,000, and if you'd like LabView on top of that, that's an extra $1,000. So alright, so let's try some tests with it. So I have it hooked up to a milligram balance that I've hacked, and internally there's a SPI bus in here that I've brought out to a connector, and I'm probing the SPI bus with the 2 analog channels. So let's take a look at the bundled app that comes with it. Here's the Windows application. You can see at the top we've got sort of a zoomed out view of the 2 traces, and we've got some time-based controls up here. You can also change the time base by using the mouse wheel. Here's the setup for the channels. I think that the interface is a little too plain. Like for example, if you want to change something with channel 1, there's no actual controls there until you hover over it, and then there's this tiny little 3-dot menu that pulls up the actual coupling controls for channel 1. They probably ran out of screen real estate, but I think they made a little bit too big of an effort to hide the controls. Over here we've got the function generator setup. It's got quite a voltage range. It goes from negative 12 to 12 volts. And as you can see in the app control, it's just the 3 waveforms that we have, a triangle wave, square wave, or sine wave. Down here we've got the multimeter controls, and you can select what you want to measure with the buttons here. Here we have a control for the power supply. So this button here turns on all 3 supplies. I don't believe they can be turned on and off individually, but you can set the voltages individually. I forgot to mention that the 25 volt supplies are programmable just like the 6 volt supply. So you can either use the up down keys to select a voltage, or of course you can just type in whatever you want. This corner has the digital I/O control, and so again, if we press this small menu button, we can select some of these lines to be outputs. So for example, 1 and 2 can be outputs, and then by clicking on the toggle button that it just created, we can change the digital state of those I/O lines, and it's a 3.3 volt output. I believe they're 5 volt tolerant. I think in the documentation it says that it can take up to 5 volts and they're protected against higher voltages, but you really shouldn't go above 5. It also has fairly basic oscilloscope functionality, so it's got a measurement menu where you can add these measurements to the current screen, and it's already showing the frequency of channel 1 and so on. It's also got a standard cursors menu, so we can do some time cursors. And probably the one thing that I like better about having this interface is that it's easier to position cursors on the waveform. This is a little bit, you can use the mouse wheel to kind of scroll in and out, and then the cursor can be positioned a little bit more easily right over the waveform. So as you might have guessed, I'm not a huge fan of PC-based oscilloscopes. It has some of these sort of nice features where you can, drag things around, but for example, they always seem to lack something. For example, if you drag this, it doesn't redraw for some strange reason. You have to let the button up for it to redraw. So if you actually want to inspect a signal that's quite long, this thing stores about 1 million points, I think, for a record. So as you can see in the top trace, there's this falling edge that's quite a bit ahead, so we can drag over to look at it, but we have to let the button up to see it. So if you're actually looking for glitches or something and you're dragging this thing along hoping to see them, you never will. Another strange thing is that the zoom level is tied to the time base, so if I zoom in, it's actually changing the time base as I zoom in. But you may not want to do that. You may want to keep the time base fixed and then just move your zoomed in window around within the waveform. Actually, let me try a single and see. No, see, even if it's a single, even if the acquisition is already done, it still doesn't redraw. So that actually is a bug that they might be able to fix. It does have slightly more advanced triggering, so you can trigger on a pattern and then again press this tiny little button and it comes up with digital lines that have to be in a certain state for it to trigger. I don't believe that it can trigger off of SPI or I2C messages though. I also don't see a more complex single line trigger. So for example, a pulse and then a delay or a missing pulse trigger. I don't see anything like that, and I haven't read anything that indicates it can do that. There is hope, though. I think that NI is spending quite a bit of time updating this app, and so I2C and SPI functionality was just added to that 8-line digital I/O connector fairly recently. So they are putting effort into adding features to this, and they've made a few claims on their website saying that those features will be given away for free, which is actually pretty cool. So the SPI and I2C decoding on a typical oscilloscope would cost, $1,000 from the big three. But these guys have included it as a totally free update with the VirtualBench, which is quite nice. Okay, I've connected the milligram balance up to the digital input lines and also connected this analog oscilloscope line back to the function generator. So you can see, pull the function generator offset up and down and amplitude up and down. It works pretty well. Just to show you how we might set up a trigger on this thing, we come over to trigger and change this to channel 1, and then we can pull the trigger level down like this. So I have to admit that for some things, using a graphical interface like this is better on a PC oscilloscope, but overall I still feel like it's kind of like driving a car with your windshield completely fogged up. I mean, you can do it, but you're probably going to miss something, and it's really better just to clear it off. Having like a digital phosphor effect and a really fast update and really fast responding knobs is probably the best way to look at a signal with which you're unfamiliar. And you're probably unfamiliar with it because you're using an oscilloscope to look at it. Anyway, okay, so let's turn on these digital control lines and see what we can see. So we're going to add a SPI bus, and we're not going to use chip select. And I found out that you can, if you say always active, it just disables the chip select line. And it's not decoding anything because the bus isn't set up quite right just yet. But if we expand the bus, it should show us the digital lines, and I was expecting to see something there. No trigger. So we'll change the trigger to trigger on D0, and we may as well turn off this analog line. Kind of funny, you can drag the bus around, but it snaps back to the top, so I guess that's kind of its preferred location, and I don't see any way of making these any larger. But anyway, we'll just go with it here. Okay, so the clock is D1, the data line is D0, that's MSB first. We're going to go on the rising edge of the clock, and then we can set the word size quite large. This is actually pretty cool. It goes all the way up to 32, which we're going to use. And we should be decoding. Oh, and then we'll set the idle time. So there's a long time between these 32-bit pulses, so I'm just going to set this to 1 millisecond. And as we can see, it's decoding the data up there in real time, which is good. As you can see, this protocol is a little strange, and so this first block of 8 bits is used as like a control set, and it's not changing with the weight applied to the scale. And then the next 3 sets of 8 bits are the actual data from the load sensor. And you can see it floating around here because it's such a sensitive balance. And then these last 8 bits aren't used either. So lucky for us, the scope will start decoding here, and then 32 bits later is the end of the data. So we're actually getting, we would actually like to just decode these middle 24, and that's very hard to set up without chip select. So my opinion is that it's good for a PC oscilloscope, but it's still a PC oscilloscope. It doesn't bother me very much, though, because I think that this device is really best suited for data logging and sensor integration. So let's talk a bit more about what it can do with programmatic control. For this test, I've got a standard 1N4004 diode forward biased across one of the 25-volt supplies, and then I've also got the scope hooked up just to monitor the voltage across the diode. This is the evaluation version of LabView 2014, and if you aren't familiar with LabView, let me give you the 30-second explanation. The idea is that you're building a virtual instrument, and this window shows how the instrument is wired, and so you can have different modules, and each one of these modules does something, like controls the voltage coming out of the actual virtual bench that's sitting on the bench here. And then the other half of this is the front panel of this instrument that you're creating. So some of these controls are like a drop box, and that actually forms a control that the user can manipulate on this front panel. So think of it as putting together an instrument for someone else to use, although that someone else could be you yourself. It's just an easy way to operate your program through this graphical interface. I'm a pretty big fan of it. I know that people have different opinions, but it's very fast. It's sometimes limiting, and so people that would prefer to program in Python or C would cite that it's too limiting for what they do. But in terms of speed and getting stuff ready fast, it is quite good for that, especially for data acquisition and analysis. This is an example virtual instrument that I downloaded from NI and modified a little bit. And the purpose, it's got some headers below here to tell you what's going on. So this first block initializes the instrument. It takes a name. You might have multiple virtual benches connected to your computer, so this thing actually queries the user for which one you want to connect to, and you can see the list only has one because I've only got one connected. I'm not going to go into detail about how to program in LabView, but you can sort of think of this as flowing from left to right. So the next thing that happens is it queries the user for a power supply channel, and on the front panel it shows up here, and we're going to choose the plus 25 volt channel. And then all these other inputs are drop boxes or text number entries here. So the start voltage is going to be 0 volts, the current limit is going to be 100 milliamps, the end voltage is going to be 1 volt, and the number of steps is going to be 100. So what this whole thing is going to do is going to program that 25 volt power supply to start out at 0 and work its way up to 1 volt in 100 steps. And as it goes along, it's going to measure the current and voltage and then show them on a graph. So we will press the run button, and as you can see, this is the current versus voltage curve for that diode. And as you would expect at about 0.6 volts, because it's a silicon device, it starts to conduct. But you can see here it's at 0.6 volts, it's only flowing a few milliamps. And one nice thing is that we can rescale this. So this is currently 100 milliamps full scale, but we can just enter 1 here. Oops, sorry. So now it's 1 amp full scale, but if we type 1M, now it's 1 milliamp full scale. We can see at 0.6 volts, it's getting close to 1 milliamp. However, the resolution on this is quite good, so we can actually go down to 100 microamp, and now we can start to see the resolution of this thing. In fact, on the 25 volt supplies, it has 35 or 30 microamp resolution, which is quite good. So if you're doing a battery operated device, you can monitor the current consumption much more accurately than you might have guessed. 30 microamps is quite good resolution for that sort of thing. Another cool feature is that you can still use the dedicated National Instruments app to use the oscilloscope on the device while you're programmatically controlling other parts of the VirtualBench, as long as there's no overlap. So for example, if your LabView program is only using the power supply part of the device, you can start the VirtualBench program and it will disable the power supply since it's being used by LabView, but you can still have access to everything else. So I've set up the scope to single trigger at 244 millivolts, and now we'll go back to LabView and run it. And as you can see, it's generated a new plot for us, and then here's the voltage that was recorded by the scope. So you can verify that the thing is doing what you want and make sure that the power supply, it's not doing something weird. And in this case, it actually does look like something a little weird is going on. You would expect this to be 0, and then from 0 monotonically increase. It's hitting the current limit here and it's capping it. And then when it shuts down, there's quite a bit of an undershoot. So the voltage is actually going negative here according to the oscilloscope. This might just be because there's no actual resistance across the power supply. I just have a diode all by itself. So I don't know if I'd fault it quite too much for this, but this does look a little bit strange. In this setup, I have the VirtualBench connected to a breakout board that I got from Adafruit. And on the breakout board, there's a high dynamic range light sensor that talks I2C. And so the VirtualBench is powering the breakout board and we're monitoring its current use. And it's also generating I2C query commands and then reading the data from the I2C transaction. Here's the really quick and dirty virtual instrument that I whipped up just to get data out of the sensor. And so the section at the top of the screen here runs the power supply, and then the section at the bottom runs the I2C stuff. And so all it's doing is initializing the sensor, enabling the sensor, and then querying data. And so if I pass a flashlight beam across the sensor board, you can see the bottom graph is showing the light intensity values. So once we've gone this far, it's easy to take the values that LabView is getting from the I2C bus, from the sensor, and then use those values to do something else interesting, like either adjust one of the other voltages. You could have it output a different voltage out of its supply based on the light input from the sensor, or you could have it adjust its function generator, or have it trigger the scope, or all kinds of things. And so the real power of this is just having all of it kind of in one. And I realized you could connect separate pieces of equipment to LabView and accomplish almost the same thing, but this whole box costs $2,000, and you don't have to have separate drivers for each piece of equipment. I noticed that it would be really helpful to have two monitors when using the VirtualBench, one monitor for the oscilloscope display and another monitor for the LabView programming. I ended up going back to using my Tektronix oscilloscope to debug the I2C communications just because it was too difficult to flip back and forth, and so it's much easier to have a separate screen for this. And so you can see here, these are the 2 bytes that are being read from the light sensor, and so when I pass the flashlight over it, you can see the values changing there. So my conclusion is that if you just want to read and write sensor values over I2C or SPI, you're probably better off using a microcontroller development board or a bus pirate or even an Arduino. And in this case, Adafruit supplied Arduino code with that breakout board. So to get up and running quickly, it would have been far easier just to connect it to an Arduino. If you want an oscilloscope, you're probably better off buying a full-on oscilloscope with knobs and its own display. However, if you want all of these things in one box with the ability to pass data from instrument to instrument easily, I would say that the VirtualBench is actually really well suited for that. And like I say, test applications at the end of an assembly line or test applications that have to move around the lab frequently are pretty well suited to it. So I think it has a pretty niche sort of area. I know National Instruments was probably thinking that this would appeal more to engineers just getting started and needing all of this gear. But I have a feeling it's sort of better off for these interesting sort of data logging and sensor exercising sort of applications. Okay, well I hope you found that useful. See you next time. Bye.